Yeah, so it's great to see you all here. I just want to say a couple of words before we start. So we thought that given the disadvantage that we have to do these seminars online, we might as well find the upside in it in bringing together people with common interests and not having necessarily a local seminar, but just sort of by interest. Please feel free to share the links and the password with anybody who you think might be interested, and they can join us. The other thing we thought is it might work well to add a Slack tool on the website, so that if people want to continue conversation, apparently I haven't actually really used it myself, but I've heard that it's a great kind of research tool, and people can just keep talking about the seminar topic on the Slack thing, and if one has thoughts, you can contribute. So there you go. So I don't think this is set up yet, but it should be up in no time at all. And yeah, and if you have ideas for speakers, framework, we can also change the time as it goes on if it doesn't work for people, because once the teaching is over, we're unflexible. Anyway, well, so that's it. That's all I wanted to say. So wait. Miroslav, do you want to introduce the speaker, as has been our tradition?
Okay, I can do that. So today we are happy to have our first online seminar, and Thomas Creutzig, who's going to tell us about triality for W-algebras.
Yeah, thank you. Yeah, it's a pity that I can't be in Berkeley. This would have been really nice. And yeah, I don't have a fancy computer yet, so the only solution I could come up with is I wrote my notes on paper, scanned them, and will now show them to you on the screen. I actually did the same with Davis with Tudor 2 weeks ago, and it worked quite well. So please interrupt me if you have any questions. And yeah, in general, as you know, vertex algebras appear all over in modern topics of physics, and you all have also worked on this. And this talk is mainly concerned with actually work of Davide and Miroslav, who are both there. And because they introduced what is called Y-algebras, which are parameterized by 3 positive integers. And they enjoy a certain really nice triality. And I would like to come to that. But yeah, let me first follow the slides. I thought, since I'm not sure whether everybody of you has seen the definition of a VOA, I will first give it, but probably I can be very quick. So we probably all know it's the underlying, it has an underlying space of states, usually infinite dimensional vector space, together with a vacuum vector, a translation operator. And the most important data is the state field correspondence, that to every element of this vector space, we can associate a field. That means the formal power series that acts on this vector space. And then this data has to satisfy certain axioms, which I list here. So I hope you can see my mouse. And so the field corresponding to the vacuum is the identity field. Then from a field, you can go back to vectors via the state field correspondence, meaning the leading term of a field acting on a vacuum gives you the original vector back. The translation operator acts as a derivative. And then the most important axiom is the locality axiom. This means the commutator of 2 fields vanishes if you multiply it by a sufficiently large power of z minus w, which you should view as that the commutator is some kind of distribution localized at z equals w. And vertex algebras, for our purposes, are interesting because of the main example. So the main vertex algebras, they are associated to finite dimensional Lie algebras, or more generally, finite dimensional Lie superalgebras via affine vertex algebras and W-algebras. So I will now quickly recall the definition. So because actually we use this W-algebras in quite some generality that is maybe a little bit unusual. So the setup is as follows. We have a finite dimensional Lie superalgebra that I denote by G, together with an invariant supersymmetric bilinear form. And then we affinize in the usual way. So we look at the loop algebra centrally extended. Also a derivation comes with it. The commutator here is listed here. And what is important is it comes with a central extension, so a central element that I denote by K. The point is that to an affine Lie superalgebra, you can associate an affine vertex algebra. So in order to define this, I have to tell you what is the underlying space of state. So for this, you first define the positive part of the affine Lie algebra, G hat plus, and then you consider the one-dimensional module for G hat plus, on which everything acts as 0 except the central element acts by the scalar k. The scalar k we then call the level of the affine vertex superalgebra. And then we let all the negative part, all the negative modes act freely. And this is then, I use the notation V upper index kg for the universal affine vertex superalgebra associated to G. And usually we omit the B for the bilinear form because we use some standard normalization for that. And I'm here quite quick because I'm sure that most of you know this. But if you want me to slow down, please let me know. So then
I should just say one thing.
Yeah.
The feature of the Berkeley seminar that we cherish very much is that there were like tons of questions. So I please do invite people to ask questions, you know.
Yeah. Yeah, please ask a question. And I'm here with the very two first slides. I'm not sure whether I'm boring you. This is why I'm a little bit faster.
I specifically have known to embarrass myself many times over, so and that's okay. Everybody knows that.
Yeah.
So it's okay.
So really the main point here I want to make at the beginning is I just review the standard construction of vertex algebras associated to Lie algebras. And if you haven't seen this, this is the construction that you learn very early in a textbook. And if you have seen it, it will become more interesting very soon. So one point of this affine vertex superalgebra is, of course, it's a vertex algebra, so we are mostly interested in the fields. And the most important fields are the ones that I denote here by x of z. So where x denotes an element of the Lie superalgebra, and it's the field associated to the -1 to mode acting on the vacuum. And these are the so in physics often it's also written as j of x of z, where x is then maybe a basis element of the Lie superalgebra. And these fields have a very nice operator product expansion, namely a second order pole that is given by the pairing of x and y times the level, and then the first order pole is just given by the commutator of the elements x and y. And from this field, you can go back to the affine Lie superalgebra, namely if you look at its mode expansions, the modes satisfy the commutation relations of the affine Lie superalgebra. And these are the most important fields because it turns out every other field of this vertex superalgebra is nothing but a normally ordered polynomial in this field in its derivatives. So in this sense, these are strong generators and every other field is recovered of those. So this finishes the review of affine Lie superalgebras. And what I told you is to every finite dimensional simple Lie superalgebra with bilinear form and choice of complex number, you can associate a vertex superalgebra. And now we want to have, we are interested in more vertex algebras that don't have such an obvious relation to Lie algebras or Lie superalgebras, and these are the W-algebras. And they are constructed from affine vertex algebras or superalgebras. Namely, what you do is you choose one additional data, namely and what I call F. F stands for the F of an SL2 triple. It is a nilpotent even element inside the Lie superalgebra. And given such an F, there's a nice way to associate a complex to the affine vertex superalgebra that I just denote by VKG times CF. And then the homology of this complex is called the universal W-algebra of G associated to F. The one that you probably know very well, so the best one is if we take G to be SL2, then we take F, the F of the SL2, and then the W-algebra is the Virasoro algebra. More generally, if I take G to be SLN and F a principal nilpotent element, then I get the very well-known WN algebra. So W3, for example, is Zamolodchikov's W3 algebra. And in general, this WN algebra is a vertex algebra that has fields in conformal weight 2, 3, 4, up to n. And these strongly generate the vertex algebra in the sense that every other field can be written as a normally ordered polynomial in these ones. However, you're not restricted to take G to be SLN or G to be a Lie algebra. You can also take a Lie superalgebra. And you also don't have to take F to be principal nilpotent. You can take other nilpotent elements. So this means this, this construction gives you a zoo of W-algebras. And these are the ones we are interested in this talk. W superalgebras associated to SLN and SLN/M. So this is why I'm also talking about superalgebras, because we also go to W-algebras associated to Lie superalgebras. Are there any questions?
Yeah.
Yes, I have one question, sorry. Can you go up a little bit?
Yes.
So have you explained how to define this Y for this vertex algebra?
You
told us the OPE. Is that?
Yeah, I have been here short. I mean, I did not tell you how to define it.
Okay, you just
but for this special Y, it's can you see it? It's
yeah, I can see your mouse. Yes.
This is what I call X of Z. So it's defined to be the sum over the integers xn z to the minus n minus 1, where xn is shorthand for x times t to the n.
Okay. And okay, great. Another question is like, can you go down a little bit? This CF on the rightmost.
Yeah.
What is that?
That is a certain complex. It's a certain free field vertex superalgebra. So that on this affine vertex algebra, VKG times this complex, you have a differential that I denote here by D. And so then if you have this differential, you can take the homology. And the homology inherits a vertex algebra structure. And this is what is called the W-algebra.
Okay.
So is this correlated to the screening current construction? Like you have screening charges, and is this complex related to this?
Yes, it is. Yeah. So in general, the vertex algebra that is obvious to construct is this affine vertex superalgebra that I shortly introduced here. And then there are a few standard techniques, and one is as a cohomology or as a homology, and this is the construct, or that's how I would define a W-algebra. Other people would define it as the kernel of certain screening charges, and one can show that the two definitions are equivalent, at least generically, and the reason is that this homology has a certain filtration, and in the degree 0 piece, you can characterize as the kernel of screenings. And for generic level, the degree 0 piece is isomorphic to the W-algebra itself. And this isomorphism is called the Muir map, usually. Okay, so, yeah, and so in general, if you look for W-algebras, you might come up with three seemingly very different looking notions. So the one I introduced as a certain homology or cohomology associated to an affine vertex algebra. Probably in physics, at least, the standard way to introduce it would be as a kernel of screening charges on a free field algebra. And then often one also introduces it as a coset. This means as a commutant, as a subalgebra of some larger structure, commuting with another substructure. And I will come to that. Okay.
I wanted to clarify what you meant by even.
Yes.
You mean that in the superalgebra sense, or in the sense of having even eigenvalues under bracket?
No, I meant it's an even element in the superalgebras sense. So it's
okay.
This superalgebra is graded by parity, and it's in the even part.
Okay.
So in all known cases, you'll have some free field formalism. Is that true?
Yes, this is a general theorem by Naoki Genra, who showed that what we know very well for the Wn algebras works in general for any evenly potent element of a superalgebra. But actually, I should back up, not quite. You always have a realization. So these W algebras often have an affine subalgebra, and what you will have is a free field realization in not quite, so inside an affine vertex algebra times some free field algebra. It's not completely free. Yeah. So yeah. More questions?
When you come to string theory general realizations of this, will you explain what those cases are which don't have free field realization? Like just purely free fields, what the free field stands.
Yeah, okay. Let me okay. Let me expand. Come back now. So the screening realization is this mirror map, which realizes the W algebra as the kernel of screening on some simpler vertex algebra. For the Wn algebra, the simpler vertex algebra is just n-1 free bosons. So a very nice free field algebra. For other W algebras, but the Wn algebra is special because it has no fields of conformal weight 1. Other W algebras might have fields of conformal weight 1. And in that case, this free field, this realization is given in terms of an affine vertex algebra corresponding to this weight 1 subspace times a bunch of further free fields. However, of course, this affine vertex algebra itself, you can also realize via free fields. So what I said 3 minutes ago was false. So that means you can always realize it in terms of free fields. Just the realization will look more and more complicated. Yeah, and I will not give any free field realizations at all in this talk. Okay, and so these W algebras have 3 constructions, and each construction has an advantage and, of course, also different disadvantages. So this homological approach has the advantage that it's very clean, but maybe not so accessible. But what it immediately does, it gives you modules for free, because if I have now a module for the affine vertex algebra, I can tensor it with this CF, this complex, and take the homology of this module, and this immediately gives me a module of the W algebra. So this is very nice. And usually the type of modules you like to look at for the affine vertex algebras are those that come from finite dimensional highest weight representations of your Lie algebra or Lie superalgebra. And then they, via this quantum Hamiltonian reduction, you get modules of the W algebra. And in physics, you usually call these degenerate representation. So, or you could also say non-generic ones. They are somehow very special. So what it is tells us, especially kind of to every finite dimensional module of our Lie algebra, we can first of all induce it to a module of the affine Lie algebra, and then hence of the affine vertex algebra, and then via this homological approach to a module of the W algebra. And this is what we strongly believe, that these types of module have a lot, representation theory-wise, a lot to do with the representation theory, well, of the Kashtan-Lustig category of the Lie algebra. Okay, so these first two slides were thought about as telling you a little bit about the basic setup, that you have seen the definition of a vertex algebra, of affine vertex algebra, and a little bit about W algebras. Now I want to back off and just recall why vertex algebras are interesting. So the short name for vertex algebra is VOA, vertex operator algebra. And if you open a textbook, it will always tell you, well, vertex algebras are interesting because they prove monstrous moonshine conjecture, and which was a long time ago in the early 90s. And this is actually very string theory related, because this monster moonshine VOA you should view as an example of a conformal field theory for bosonic string, and then what Borchers actually did is he was looking at a related associated VRST cohomology of physical states, which had certain nice properties that allowed him to prove the moonshine. So historically, at least as a mathematician, you would say VOA are interesting because they were an essential ingredient for an important conjecture. And nowadays, we say vertex algebras are interesting because they appear as very, very rich invariants of higher dimensional structures. They appear as invariants of 3-dimensional and 4-dimensional supersymmetric gauge theories. They appear, they are important in low-dimensional topology. They are meaning, especially in 3- and 4-dimensional topology. So there's a super nice paper by Gukov and Fagan that explains how to associate vertex algebras and their categories to 4 manifolds with 3-dimensional boundaries. And yeah, it's really exciting how many nice applications we have. And the original string theory relation of vertex algebras is that a vertex algebra is the 2-dimensional chiral algebra, the 2-dimensional symmetry algebra of a 2-dimensional conformal field theory, and the 2-dimensional conformal field theory describes the worldsheet of a string propagating through space-time. So to the higher dimensional physics, I actually learned that from Davide. He explained to me how vertex algebras and their tensor categories are very rich invariants of 4-dimensional supersymmetric GL, geometric Langlands twisted gauge theories. And this is actually the context I now want to talk about. So what Davide explained to me is that we had a setup that is illustrated in this picture, very, very roughly. So we have the 4-dimensional gauge theory, and we think about it as having 3-dimensional topological boundary conditions in there, and they can intersect, and the intersection is 2-dimensional. And all this data is related to vertex algebra in the sense that we can have categories of line defects ending on the boundary conditions. And these line defects we think about as being the fields corresponding to modules of a vertex algebra. and on the intersection of the boundary conditions, only local fields. That means fields that form a vertex algebra can lie, and then depending on what kind of boundary conditions, one has a corresponding vertex algebra and a corresponding category of module sitting, and this is I found this very interesting because this picture immediately gives a zoo of super exciting new conjectures about vertex algebras, about representation categories of vertex algebras, about how seemingly very different vertex algebras are related. And actually one of the most exciting pictures in this game is I think the Y-algebra conjecture of Davide and Miroslav. So for that, the picture becomes a little bit more fancy than this one. So this is on the next slide here. This is the picture of Davide and Miroslav. So they are looking at, again, at GL twisted n equals 4 supersymmetric Young-Mills theory. And now here they have 3 interfaces and with 3 gauge theories with different gauge groups, UL, UN, UM. So L, N, and M don't have to be the same. And then now this so gauge theory comes with a coupling, which is always denoted by psi, and then their proposal is again that VOAs appear in a very meaningful way. So first of all, categories of line defects again end on these interfaces, and on the intersection of those we have a VOA sitting. And because of this picture, if you look from the front of it, it has the shape of a Y. They call it the Y-algebra or the YLMN algebra because it's labeled by these 3 positive integers LMN.
So why do you just take 3 interfaces? Why not put an arbitrary number of that? Why just take 3 of these things, not some?
Yeah, you can do an arbitrary number, and then you will also, but then also understanding what's going on is more complicated. So I want to comment on your question at the end of the talk. Okay.
Okay.
It's it's a very good question. It's so yeah. Let's focus on 3 and discuss your question at the end of the talk.
In that case, can you pull them apart if you have more than 3 so that it will still have intersection of 3 in every, and then they will like join as a web or something?
Yeah, exactly. This is what you would like to do. So you would like to say if you have 4 interfaces, you think about them as 3 glued with 3, and then glued together. So the idea is a configuration with 4 interfaces you get by gluing 2 with 3 interfaces. And then you can do successive gluing to get more and more. But the question is, of course, how do you do this gluing, whether this is possible. And yeah, I would like to come back to this at the end of the talk, okay?
Is it important for you, what you said about the modules of the algebra and their geometric realization was a little bit strange. At least I would have thought that the sort of there are special classes of modules that are not allowed to, and that are not allowed to move away into the, like if you can move just a slide before.
Yeah.
That are not allowed to be anywhere. I mean, sure, in string theory, there are lots of objects you could in principle consider. But so for example, in some string theory realizations of this, you'll have symmetries that basically, if you think about this, like this Y algebra is coming from some C3, the symmetries that rotate the complex planes in the C3 are really important. And any defect that looks like what you drew is going to break that. So it might arise, but for many questions that you'd want, for example, if you wanted to understand just like finite dimensional representations of SLN hat, or all the degenerate and non-degenerate representations of W-algebras, I wouldn't think you would want those. I would have thought you want things which kind of just in terms of this Y that one draws that run along the legs of the Y and don't leave them.
Yeah, I think that's correct.
Okay, I see. Okay.
Yeah,
I mean, you can have surface defects, right?
Yes, but they are then.
You can have surface defects that also fill some faces. That's true, but they wouldn't break the symmetries. They wouldn't just be anywhere.
Yeah, and they would correspond to more complicated modules.
Sure.
Much more complicated ones. Right, Davide?
I don't know if, I mean, I don't know, more complicated, perhaps simpler.
Okay, it depends on what one means, but
surface defects should be like non-degenerate representations of W.
Yeah,
right? I mean, just like these generic ones.
Yeah, they should be generic ones, but then from a representation theoretical point of view, the non-generic ones are actually quite hard to understand. This is what I meant with so for example, for me, the guiding example is always just an affine vertex algebra itself, kind of the simplest type of W algebra. And in that case, the non-generic ones are these relaxed ties weight modules. This means they have already infinite dimensional top level subspace. Yeah. And they are just hard to understand in many respects, but yeah. Okay, yeah, let me go on. If you look at this interface, what one should, of course, believe is that it doesn't matter where I put my L, M, and N, in which order I put it. What Davide and Miroslav say is that this configuration should have an S3 permutation symmetry. Of course, then another permutation, also the coupling will change in a certain way.
I would have thought that there should be an obvious cyclic group symmetry, but the reflections are less. I mean, why there should be S3 symmetry is less obvious to me.
Yeah. So if you look at the paper by Davide and Miroslav, they say there's an S3 in symmetry. This means we have 6 isomorphisms between different Y algebras, and a few of them are obvious ones. And then there are two non-trivial type of isomorphisms. Yeah. Let me maybe give the first example, because it already tells us. So the first example is if I take a UN and then the L and M both equal to 0. So kind of simplest setup. And this setup is already highly interesting. So then, because there already we see that the triality conjecture of Davide and Miroslav is generalizes something very interesting vastly. So the YN00 algebra is just the diagonal SLN coset. So here in the first line, I wrote the mathematician's notion of it. What it means is I have the affine vertex algebra of SLN at a certain level. So it's now here, the notation is a little bit clumsy because it's expressed in terms of the psi of the coupling of the gauge theory times the basic representation of SLN. And then I take the diagonal coset, and the physicist has this nice suggestive notation. I take SLN hat at one level plus at the other level, and then the diagonal coset by it. Anyway, these two mean the same thing, physics and mathematicians notation. So this is the diagonal coset realization of the WN algebra. And then if we take the Y0N0 algebra, it is actually defined as the principal W algebra, as the WN algebra of SLN. So for example, at case n equals 2 is just the Virasoro algebra, or the case n equals 3 is Samologichov's W3 algebra. And if I take the last label to be non-zero, it's also defined as the principal W algebra.
So this is the case where in your original picture, I have the U0 theory, the U0 theory, and the UN theory?
Yeah.
So then is the interface between the U0 theory and the U0 theory also, by the U0 theory, I suppose I mean just the trivial theory?
Yeah.
And is the interface also trivial, or is it some freestanding three-dimensional field theory?
I think it's also trivial, but maybe Davide can say more.
Sorry. Can I repeat the question?
The question was for the 0 and 0 thing. It's kind of U0, U0, and UN, right? So yes. I suppose U0 just means the trivial theory. And then is the interface between them also trivial, or is it some 3D field theory?
Well, it's a boundary condition. So it cannot be trivial.
The interface between the 0 and the n is not trivial, but there's...
between 0 and 0, well, yeah, it's you're right. It could have been a 3D theory, in principle.
But it's not.
But it's not. As far as I know, it's just the trivial object.
Yeah, good, thanks.
So the junction is a junction between Neumann and Dirichlet without extra 3D degrees of freedom coming from the side.
Oh, it's between Neumann and Dirichlet. Oh, so the two boundary conditions on
Nampol, sorry, not Dirichlet, Nampol, Neumann and Nampol.
Okay, okay. So just a line defect living on this fixed boundary condition.
It's not a line, it's a surface, right?
Oh, surface, sorry. Yeah, surface.
So there is Neumann and Nam coming together.
Now I'm confused. In the picture before, there were these three interfaces.
Yes.
Are you saying those three interfaces are of different kinds?
Can you say it again?
So there's three three-dimensional interfaces in this picture.
Yes.
What was Davide saying about some of them being Neumann and some of them being Nampol? I didn't understand this point of how the different kinds of interfaces.
I was just giving a name to the interfaces. So Thomas didn't name these interfaces, right? It did not say which interface is there between the three.
Yeah, that's right. Yeah.
So I was just giving a name to them.
But I think there are three different names to them, or the same name to all three of them, or like.
It's
the boundary conditions, right?
Yeah, there are three different names.
But it's the same thing sitting there, but there are different boundary conditions from different parts, right?
More precisely, so there is a family of interfaces labeled by two integers, two coprime integers. And in this picture here, the integers are something like 1, 0, 0, 1, 1, 1.
Are these integers in general determined from L, M, and N, or are there extra data?
No, it's an extra piece of information. Here, you're looking at a picture for 0, 1, 1, 0, and 1, 1, and that's it.
I see. And that's also, and that's also why the definitions of yn00, y0n0, and y00n are asymmetric, because.
Correct.
Thanks.
At the same time, I think it will be helpful for Vivek to know that you can get basically the same system if you start in M theory on C3 and you put M5 rings on, say, you take C3 with coordinates like Z1, Z2, Z3, and you set M5 rings on the three obvious divisors. On Z1 is 0, Z2 is 0, Z3 is 0, and these are the numbers you get. And the conformal field theory, I think David and certainly David and Miroslav explained this already, I think, in the original paper. The conformal field theory he's describing is what lives at the intersection. So you take three divisors in C3. What's left is, I guess, a common intersection transfers to the Calabi-Yau. And that's where
But from that point of view, how does this asymmetry appear? One of them being called 1, 0, one of them called 0, 1, and one of them being
well,
called
M-theory tells you that they have to all be the same, and how they how does this 1, 0, 0, 1? This is just like you know, in toric reduction, like if you reduce on the T2, right, it tells you like which leg of the C3 on the T2, which leg. This is just the same story. So
thanks.
Yeah, by the time you go to Yamil's theory, the two circles or the torus were used differently.
I see. Thanks.
Yeah, thanks. So yeah, as Mina just said, these Y algebras, they should be the same from physics reasoning. However, if you just see their definition as vertex algebras, this seems to be rather strange. And this is where I just stopped 5 minutes ago to say that to illustrate this in the simplest example, because there the yn00 algebra is defined as a certain coset, while the 0n0 and 00n algebras are defined as W-algebras on the nose. And then there is this triality. This means an S3 of isomorphisms. And indeed, we know two non-trivial isomorphisms. The first one is the famous Fagan-Frankel duality, which tells us that the W-algebra of SLN at shifted level psi and psi inverse are isomorphic. So in this psi in physics is often also called B or B squared. And if you remember the formula for the Virasoro central charge is of the form 13 minus 6b minus 6b inverse. So it has an obvious B to B inverse symmetry. And this also holds for general principal W algebras and is called Fagan-Frankel duality. And then that the principal W algebra of SLN can also be realized as a coset is some kind of generalization of the famous GKO coset construction of the Virasoro algebra. It has been known for a long time in physics, but has been very hard to prove. And Tomiyuki Arakawa, Andrew Linshaw, and I, we did this 2 years ago. So yeah, so these are actually already for the 0-0 case, highly non-trivial statements.
Can I ask you a question?
Yeah.
So this is about Mina's comment earlier about how you can get this from some reduction of a C3 geometry. As was pointed out, in that C3 setting, everything is completely symmetric. So one might imagine you can prove all of this by constructing these vertex algebras out of whatever the Donaldson-Thomas moduli spaces for that C3 geometry. Is that something which is done or expected or no? What's the...
I can comment on that. Yes, you can. You can take the cohomological whole algebra associated to C3, which is manifestly triality invariant under the permutation of the C's, and you can let it act on moduli spaces of framed quiver, where the framing is exactly associated to putting those extra M fibranes that Mina mentioned earlier to the setup. And you can let the cohomological whole algebra act on this moduli space. It's going to be completely triality symmetric, and you can just prove or show that the algebra that you're going to get is isomorphic to the algebras defined here, or via some in terms of some free pluralization that was also mentioned earlier.
In the sense that, so you can prove that it's a truncation of W1 plus infinity, but has it been proven that these YLM as defined on the board are the same as the truncations?
So I think currently there's no proof that the free pluralization of the algebras are the same as the as the quantum Hamiltonian reduction that Thomas is talking about.
Yeah, they're
but is it proven?
I mean, yeah, there are quite a few subtle issues. I mean, that's the theorem on the next slide that is proven.
Okay, well, anyway, so if we assume that these two are the same, then we do have a proof that the algebras that you get from this geometric realization is the one that you get from the free realization.
Right, and
perhaps I should add another couple words on another approach. So Kevin has given information on how to think about omega deformation of M theory. And in principle, you can use Kevin's arguments to convince yourself that these Y-algebras must have a third definition as truncations of a W1 plus infinity algebra. But I don't know how much this perspective is proven.
Yeah,
in terms of relating these.
Yeah. I mean, exactly these things are the ones we are working on at the moment. And well, why don't you let me go on, and you see what I have to say, and I will comment a little bit on the proof because it goes exactly in this direction. Okay. So, any other question? Okay. Okay, I will now start actually to define a few Y-algebras. Remember, I told you that W-algebras are characterized by nilpotent elements, but nilpotent elements for SLN are in one-to-one correspondence to partitions of the integer n, and partitions you can nicely describe by Young tableaus with n boxes. And the nilpotent elements we are all interested in are the ones which have a single large column and one row. So the height of the column is n, and the length of the row is m, and we call the nilpotent element Fn, m. And these Y-algebras are actually related to super W-algebras. So for that, you consider SLN/m, and there it's the same thing. Nilpotent elements are characterized by partitions of the pair of integers n and m, which are characterized by pairs of Young tableaus. And so then the corresponding nilpotent element I call Fn/m. If we have the partition of n is just a single column and the one of m a single row. So these nilpotent elements ensure that the corresponding W-algebra has an subalgebra that is an affine vertex algebra of type GLM. So this is what this row tells us. Let's go on. Here is now the definition of the Y-algebras actually. So the first one we call C psi n, m. So these are the ones that you get from the W-algebras. So you choose the nilpotent element such that the W-algebra has an affine GLM, so you can take the coset. The coset is defined to be what we call C psi n, m algebra. And similarly, if you take the W superalgebra, again, the nilpotent element is chosen in such a way that we have an affine GLM subalgebra, and so we can take the coset. And this coset is called D psi n, m, which is just our notation. And let me now, relating to Miroslav and David's notation, it is that the D psi n, L corresponds to the YL0n algebra and the C psi to the Y0m, n algebra. And so this means one type of Y-algebra is defined as a coset of a W-algebra, the other one as a coset of a W superalgebra. Okay, and then David and Miroslav predict a lot of trialities that are really highly non-trivial. And the theorem of Andrew Linshaw and myself is that it's this one, is that these triality conjectures are actually true. This means here we have a coset of a W superalgebra of type SLN/m, and it's isomorphic to a coset of a W algebra of type I think I should have written here an M of type SLN, and the relation between the shifted levels is exactly the Fagan-Frankel duality. And similarly, there is an isomorphism between cosets of W superalgebras of type n/m and m/n, where the levels are related by this nice S-duality relation. And this relation actually has a very nice explanation from S-duality, but that's a whole other story. So what Andy and I are able is we are able to prove these conjectures of Davide and Miroslav. And let me maybe, since there was quite a lot of discussion about how these W algebras arise, sketch the main the main ideas of the proof. So first, one has to prove what type these Y algebras are. And for this, we go to a large psi limit, and we explain how one can solve this large psi limit as an orbifold problem that tells us these cosets are algebras of a certain type, and it will always be of type 2, 3, 4 up to some large bound. Okay, so then as a next thing is we show that the coset must be a quotient, must be an extension of a quotient of W infinity, this 2-parameter family of W algebras, and then we give a reconstruction argument that this is only possible if this quotient is a certain 1-parameter quotient. So this W infinity algebra is a 2-parameter family of VOA generated VOAs generated by fields in conformal weight 2, 3, 4, 5 up to infinity. And you have now to ask the question: can you extend this one by tensoring it with an affine GLM and then by fields of given conformal weight to a W algebra of a VOA of this W superalgebra type? And we can prove that this is possible if and only if one is considering a certain 1-parameter subfamily. So this proves that these cosets are at worst extensions of what we conjecture it to be, and then we can look at special points, and that they allow us to conclude that these extensions are impossible. I mean, there are no non-trivial extensions. So it's anyway.
Special points in psi.
Can you say it again?
When you say special points, do you mean special values of psi?
Yeah, special values of psi. Yes, you have very nice coincidences where they correspond to principal W algebras of type A, actually rational ones where you know. I mean, yeah, you have this. You use this special coincidences. Yeah, so what it gives is, of course, I mean, if you're a physicist, you knew this statement is true because this is what physics is predicting, but we can give a formal proof of it.
So the embedding in W1 plus infinity is really playing an important role in the proof.
A very important role in the proof, yeah. So what we kind of prove is that conversely, you could ask the following question: given W infinity, given your favorite affine VOA, it has to be GLM, and your favorite integer, for example, 7 or so, can I extend W infinity times affine GLM by fields in the standard representation of conformal weight 7? And then the answer is yes, but you have to restrict to this very special 1-parameter subfamily. And so the argument relies strongly on having a very good understanding of W infinity. And so, actually,
do you use the braiding properties of degenerate modules W?
No, not at all. No, it's no. That would be a nicer argument, but we don't have good control over that. Yeah, I mean, I would like to prove it that way, but I can't. The same. David and Miroslav have a similar type of conjecture for orthosymplectic superalgebras, and the same type of proof should apply as well. But our paper is already 80 pages long, and it's just tedious, so we will do it next year. But I'm quite excited. I mean, I'm not quite. I'm really excited about it because it opens the doors to do many more things. So I think I wanted to conclude with an outlook why this is interesting from various perspectives. So if you like representation categories, then you might like to ask what does this observation, this our theorem, tell us about possible categories of modules that this W-algebra has, or this coset has. And so the idea is VOA extensions are possible if and only if one has an equivalence of corresponding tensor categories. So these W-algebras, they are extensions of an affine GLM together with this coset algebra. This means the belief, and this belief is actually a theorem under certain conditions, is that this coset must have a category of modules that is equivalent to a Kashtan-Lustig category of GLM or SLM. Let's say SLM here at a certain level. But since we have this our triality isomorphisms, we can construct it as a GLM and a GLN coset. So this means simply the representation theory of VOAs, our theory of VOA tells us this Y-algebra should have two Kashtan-Lustig categories as categories of degenerate modules, one of type SLM and one of type SLN. And this would be a theorem if one could show that these non-degenerate modules form, these degenerate modules form a tensor category. So to go to the simplest example, that would be
Can I ask a question?
Yeah.
Why doesn't it have three categories of modules corresponding to three legs?
Because it's now the YLM0 algebra. One label is still 0.
I know, but still, you would have the non-trivial defects that run along all three legs. The same way, if for the 0, 0, n, there are two categories of degenerate modules related by this Fagan-Frankel.
Yeah,
there should be an SLN/M too. Coming from the.
You're right. You would expect a third one. I am right. You're right. There would be a category of a superalgebra. I didn't include it. But yeah. So I now only included those which come from the coset construction in the statement. Yeah. But to give an example, if we take M is equal to N and the special case of the Y00N algebra, where the W algebra is just the principal W algebra, we know a principal W algebra at shifted level psi and psi inverse are isomorphic. And indeed, we also know the W algebra has a Kashtan-Lustig category of SLN at level psi and psi inverse. So this is would be an example of this. And this point, this is a direction I really want to pursue, and it's also quite important to the comments I got from you concerning Y, L, M, N, R, S, P, Q, and so on algebras with many more interfaces. You think about them as gluing Y algebras, right? You could now take a YLMN algebra times a YL prime M prime N prime algebra. And we could ask ourselves, can we extend them? And the same philosophy applies, that applies for the coset constructions. Gluings of VUAs are possible if and only if the categories of degenerate modules can hold hands. You can glue them in such a way that the braiding becomes non-trivial, trivial, so that you get a local extension. So that, yeah. But then in that way, you would, for example, believe that you can, and Miroslav has already written papers on that, you can, or was it too much? Anyway, that you can extend products of Y-algebras to larger structures. Yeah, I haven't talked about YLMN algebras actually, but I have a super nice observation which I want to work on next. So there's a procedure which I call
about the gluing, right? So the gluing, the result of the gluing should not depend on the order, right? Like on the topology of this web.
No, it shouldn't, exactly.
What's the significance of that?
What is what?
What does it mean in terms of representation theory or categories of modules?
Yeah, it means right. It is this that you really have the Deligne product of the two categories. This means the left category here, the operators are local with respect to the right ones, and so this means if I have now my web, I want to do successive gluings, and it shouldn't depend on the order. And what it means is I do one gluing, then for example on the right category, and then the left category becomes also a category of modules of the larger structure, so that you can use it for gluing again.
Oh, I see. So it's encoded here. Okay.
Yeah, it's encoded there. It's a locality property. It's really in this Deligne product sign here. Okay, I'm already a lot over time. Let me just give you this one comment on the YLMN algebra, okay? So I only have said, Andy and I, we only have a theorem about the YLM0 algebras, one label being 0. But and the general YLMN algebras are more complicated because actually you have to take W superalgebras and then coset by affine vertex superalgebras, and structure becomes tricky. And actually we believe that these cosets are not even simple as vertex algebras. But there exists a very nice procedure which I call cohomological reduction, and others call Duflo-Zerganova functor, which, for example, which means you take a superalgebra and you take a nilpotent odd element, call it Q, so it squares to 0. But an odd element that squares to 0, we can take cohomology of that one. And so if you do this, for example, for SLM/N and you choose Q appropriately, you get as cohomology SLM-1/N-1. So you can use this cohomology to reduce the rank. It turns out you can also do this for affine vertex superalgebras and then for W superalgebras. And it looks like it seems to be possible to use this kind of cohomological reduction of superalgebras to give a very nice relation of YLMN algebras to YL-1M-1N-1 algebras, so that eventually you end up with an YLM0 algebra, one label being 0. So you have a kind of nice functor, this Duflo-Zerganova functor for W superalgebras that descends down to a YLM0 algebra. Okay, I'm a lot over time, sorry. Thank you very much for your attention.
Thank you, this is great. The fact that these cascades that you talked about in the end exist, in some sense that this is clear from string theory, right? Because this while and M, in string theory construction, it's clear that you can separate all the branes. So you can peel them off one by one, in fact, right. I mean, I suppose that's why the free field formalism exists, right? It's just the separating of the branes in the extra dimensions which you have, which
I
get you to free field.
I understand that this should be quite clear. It's I think actually also my observation is even on the VOA side not such a complicated one. But it's quite interesting.
But what is the relation with this when you take this this functor which makes LM and then less by unit? Like, are these algebras really equivalent to each other?
No, not at all. It means it means there exists a certain you start with a YLMN algebra, and you can realize the YL minus 1 M minus 1 N minus 1 algebra as a cohomology. This means
but what does it mean, for example, for representation theory? Like, can I obtain one from another?
That means you have a functor from the representation category of the LMN algebra to the L minus 1 M minus 1 N minus 1 algebra. This functor will have a huge kernel, so it will.
I see.
That's also probably this idea from the cascade. The larger LMN, the more complicated the object, and but at least you have this nice functor that makes it simpler, until you end up with something that we know from Lie theory.
Okay.
So it looks like you can do interesting things by embedding these algebras into what W1 plus infinity. Now, mathematically, is there any notion of what are the possible generalizations of W1 plus infinity? I mean, is there some nice class of,
Yes.
Objects?
Yes, there is. This is of course getting very. So there are two directions you would like to go, so these. What you do is you start with your well-known object, and in this case, our well-known object was the Wn algebra, and you ask yourself, can I embed it in a nice, larger structure that unifies it somehow? And that leads to this two-parameter family of W infinity algebras. And now there are the two generalizations that I know of. Is first of all, you can ask about diagonal cosets if you can generalize it. So you could take, for example, SLN at level K times SLN at level L and diagonal coset. So this would depend on the parameters K and L and N for the SLN. And it's pretty clear. That there exists a 3-parameter family of VOAs that interpolates between them. So it has all SLN cosets as 2-parameter subfamilies. So that's one structure that exists. I'm not so sure how interesting it is for practical purpose. The one people are much more excited about is the rectangular type. What can I say about those?
Some of them clearly come from string theorem theory, like you mentioned the even version of W1 plus infinity, symplectic groups. If I look at toric labials without internal faces, I can get all sorts of other
exactly.
Like algebras which control the glued, which come from gluing multiple W1 plus infinities.
Yeah, exactly. They come from gluing multiple W infinities, but then that picture is much clearer.
But I was just wondering if there is something else that can teach us things we don't know.
Yeah, there's actually there are new things. So Miroslav and I have been talking about a little bit about this. So somehow D21 alpha is a very good guideline, right? Because D21 alpha is the only, the very, very exceptionally superalgebra. It's a one parameter family of Lie superalgebras based on 3 copies of SL2.
Mm-hmm.
And so this means it gives us so this means it gives us on the nose a 2-parameter family of vertex algebras, namely the vertex algebra of D to 1 alpha at level k, so alpha and k are 2 parameters. And it seems that higher rank generalizations of the structure exist. So for example, there should exist an object that is D to 1 alpha like, but based on SL3, SL4, and so on. And I think actually, yeah, but they and they are general, but they are probably related to diagonal SLN cosets.
Mm-hmm.
So this is a family that's not much known, but I'm also not so sure how interesting it will be because.
Another question: do the Q deformation of these algebras play any role for the sort of things you're interested in?
Which ones?
The Q deformations of these algebras.
I haven't thought about it.
Because right, the W1 plus infinite, right, has a Q deformation to quantum toroidal algebra. I think it still has a 3-parameter truncation, although I don't know if that's true.
Mm-hmm.
Does somebody know if it's true?
I think it's true.
Yeah, there is such a thing. There is such a thing. I'm not sure in which generality this is known, but at least like everybody believes that it is there. I think.
No, but that's in math, in physics literature, right? So David is asking probably about math literature independently, right?
Isn't is the point of this discussion that whatever you did in cohomological Hall algebra you can do in some K-theoretic way? Is that the?
This would be one way to get to it. Yes.
I think this perspective is really useful because in the Q deform case from string theory, you can sort of essentially a bunch of one loop calculations sort of derive everything you want to know about these algebras, essentially, as long as like, you know, on a cylinder or on a plane, you can compute all the correlators and as some kind of gauge theoretic things. And it's quite clear so it gives you lots of insights about what are the, you know, not directly in the language you'd want for representation theory, but in terms of the answers for, you know, computing, you know, correlators of chiral vertex operators of all possible representations that I think probably has, so, including the infinite dimensional ones.
I mean, what I was saying is that by whatever construction you use to produce W1 infinity out of some cohomological Hall algebra, you might imagine you just upgrade that whole construction, which would answer your question about does that thing exist and have its truncations.
Okay.
I don't know.
Mm-hmm.
What is the construction in physics that leads to this W1 plus infinity algebra?
So Kevin has this way to understand twisted M theory and objects which can live in twisted M theory. Has this idea based on Koszul duality, which tells you that, for example, if you want to create a surface defect in this twisted M theory, you need to give me a vertex algebra equipped with a morphism from W1 plus infinity.
I see, but you can't say that W1 plus infinity itself is some algebra of operators sitting somewhere.
No, that's right. So what you have is that's right.
I see.
So in order to have this collection of 3 stacks of M fibrils which couples to M theory, whatever vertex algebra lives on these 3 stacks of M fibrils must admit a map from W1 plus infinity. Now it's not clear. The fact that this map is surjective is a priori not obvious, and it probably has some deeper meaning in terms of holography.
I think it's maybe even a little clearer in this Q deformed world. So the Q deformation, if I recall correctly, Q deformation of this W1 plus infinity, right, is this quantum toroidal algebra. And the quantum toroidal algebra has generators. So you end up basically studying M theory on a geometry that involves a torus, and the generators of the quantum toroidal algebra are just the momenta around the PQ1 cycles of the torus. So the generators of the algebra are even sort of clear in some setting. So
that's right. So quantum toroidal algebra acts on the K theory of the moduli space of instantons, right? So that's sort of the canonical statement from Schiffman and Vassirov.
Yeah, but it's just part of, in principle, it's just part of the story. Like you have, it's just one
right.
module of
one of the planes.
Yeah. So in principle, you have a richer representation theory, and you have a richer story about this quantum toroidal thing. So you can model. I believe you can model this junction somehow.
I think the torus that arises in M theory in one of its versions, it's basically how this quantum toroidal algebras were written down in the first place I guess basically algebras of VPS states of D2 branes and D0 branes on a torus. Of course, it's the same thing.
I will be careful with that because there is a very important central extension.
Right, that's right.
So what you're describing is the one that comes from M2 branes. That controls the coupling of line defects. Yeah, the precise relation between the one that controls M2 branes, the one that controls M5 branes is still very confusing to me. I've been trying to work on it with Miroslav, but we only have partial. I know they're pretty much almost the same algebras, but they're being seen in different ways.
Yeah, I mean, I think that the fact that, for example, in this in the quantum toroidal algebra, basically there should be some kind of statement that goes along the lines of that quantum toroidal algebra acts on BPS states of type 2B string theory on flat space.
Mm-hmm.
And but to sharpen this into some into something that makes sense either mathematically or physically, it's in some sense the algebra is everywhere. I think that it acts is not a question, but to actually get a precise both physical and mathematical statement is the question one wants. So it's a very nice, there's a very nice story sitting there. So just for, yeah, but I think it hasn't been chiseled out yet.
Sorry, about the central extension, isn't that simply the ratio of epsilons or exponentiated version of that gives the two central extensions of quantum toroidal? So I think
no, those are parameters, not central extensions. There are also central extensions, which you can set to 1 pretty much, or to some simple values, but unless they're 0.
So what are the central extensions? Can you say more about this?
So if you look at the quantum toroidal algebra, right, it has these generators labeled by 2 integers, P and Q, say, or A and B, whatever. And if you look at, say, the generators 1, 0 and the generator 0, minus 1, 0, so generators with opposite charge, or anyway with co-primes, with the charges that are multiple of each other, they almost commute, but they have a central term. So if I do the commutator of 1, 0 and minus 1, 0, I get a central term in the full quantum toroidal algebra. And
that's different from Q1, Q2, Q3 business. So it's something else.
And I think the central term can pretty much be set to 1 just by rescaling the generators or something like that. But I'm not quite sure in the quantum toroidal algebra, but that's definitely the case in the affine Youngian. So in the affine Youngian, there is this generator psi zero, called psi zero in the literature, which when it's non-zero can be set to 1. So I mean you don't see it when you do. So if you do when you say identify the affine Youngian to W1 plus with W1 plus infinity, you implicitly setting psi 0 to 1 or to some non-zero value. On the other hand, when you look at the algebra that lives on M2 branes and you do the Lagrangian limit, you get the affine Youngian, but with psi 0 set to 0. Which is quite different.
So I think that's just a different representation. Like if you have a like a representation with a central charge or with a zero central charge, like it's the difference between the representations of the same algebra, more or less. It's an equivalent way of saying the same thing, isn't it?
Roughly, yes. And right, so these algebras are almost the same, but when you they seem to have only one of them as a natural.
Is the seminar still going on? Why aren't you yelling at the speaker?
Sorry. So anyway, in Kevin's setup, the algebra associated to M2 branes is controlling the topological OPE, the OPE along the topological direction. And so it's an algebra. On the other hand, the one that is associated to the M5 branes is controlling the OPE in the holomorphic direction. And so it comes out as a vertex algebra. Now the precise relation between the OPE in the topological direction and the holomorphic direction, and how does this relation goes to Koszul duality are questions which I don't fully understand, whose answer I don't understand at the moment. So there is some kind of a...
But eventually the algebra should be one and the same. That's the hypothesis. That's the conjecture.
No, it's not true. The algebra for the M2 branes, unless you... Yeah, I don't think the algebra should be thought about as being the same.
Sorry, isn't it like a single bulk algebra acting on different branes or something like that?
Yeah, that's right. But it's acting in different directions, right? So there is some kind of a... The algebra in the bulk has a sort of E1 and holomorphic operations. Sort of an holomorphic analog of an E2 algebra. And now you're acting in the two different directions. And
right.
There is definitely some way to deform this operation into this operation. And I'm sure you can find some renormalization scheme where the operation is essentially the same. That's probably why the two algebras resemble each other a lot. But the details, as I'm saying, are a little bit confusing.
Excuse me? I actually had a question.
Yeah.
I think I definitely missed this, but did you identify a 3-form with triality?
A 3-form? No. No, I didn't.
Wait, so I think I'm not quite understanding how you're using the triality then. Because from what I understood, you identify a form similar to with a duality, you identify a 2-form.
I don't understand how a 3-form should come up here.
I think I'm misunderstanding that.
Yeah, yeah, maybe.
All right, any more questions? I think the progress on this problem has to be possible, because in particular there are questions about type 2B string theory in flat space, like how hard can that be?
Thomas, you had postponed one of my questions until the end of the talk, but they never arrived at it. About many of these coming together.
Yeah, this is what I meant here with the gluing.
I see.
I wanted to have this line here visible. So the idea is that the Y-algebra has certain categories of modules, of degenerate modules. And here the picture is actually, it has one category that is of type SLM type, one of SLN type. And the idea is if you have two VOAs, for example, two Y-algebras that both have a category of SLN type, and the levels match in a nice way, then you can glue these modules along this category and get a large VOA extension. And so you should picture this as you have a Y-algebra, which has 3 legs, another one, and they have one category that matches, so that you can glue along that one, and then you get you would get let's call it a glued Y-algebra. You started with one which had 2 times 3 legs. You glued on 2, so 4 legs survive, and so you would.
I mean, let me just ask. I mean, if I understood what Mina was saying correctly, this original Y, it's I should understand it as the tropical diagram of the mirror to C3. And am I supposed to similarly understand for more general toric geometries that you get some configuration, which is the toric diagram of the mirror, and that's the diagram which I'm supposed to understand this gluing in terms of?
I think so, yes.
From that point of view, why are there questions about that glue? I mean, shouldn't the physics in the same way tell you what it is you're supposed to be doing there?
Well, I mean, I think from the physics point of view, this is quite clear. Actually, it is just, that's related to a question Davida asked. So the proof of Andy and myself is very long and complicated. And ideally, there would be a much simpler proof, namely, you just glue. But you can only glue if you have sufficiently good information about the representation categories of these these degenerate modules, which you usually don't.
I see.
So it's a technically issue. So this I could now immediately say, assume my VOAs are nice enough, and I can write down the gluings. And of course, I do this in my head. I just don't do it publicly.
I see.
Yeah.
Sorry, David, what were you going to say?
A possible strategy would be to observe that if you just do the gluing at the W infinity point of view, you know the answer of the gluing as a separate object. Meaning there are predictions, at least for some of the gluings, of which sort of analog of W1 plus infinity algebra you get after gluing. So perhaps you could think of going backwards. You just say, I have this bigger algebra, which is the glued algebra. I have its truncations. These truncations, I have 2 W1 plus infinity subalgebras, which also truncate, and use that as a starting point.
Yeah, maybe. And also, our theorem is reconstructive. So this means what we do is we take W infinity, we take GLM, we glue to a larger structure. So this means there we can do the gluing, right? But now once we have done the gluing, we still have an affine GLM. We can do our favorite procedure with it. For example, we can do a quantum Hamiltonian reduction on that one, and then followed by a coset. So this means, and if we do so, then we have immediately realized constructively the gluing of 2 Y-algebras. And we can iterate, right? If we have a W-algebra reconstructed, which has a GLM where M is very large, I can, of course, split M in a large partition and do it step by step. And so this means our setup is good enough to realize many gluings, but unfortunately not all of them. And so, but as David said, it will give us examples of larger structures which are glued W infinities, and maybe from that one we can go on and guess further gluings.
Okay, so any more questions? Okay, so thank you everyone. Is there one? No. So thank you everyone for joining us tonight, or today. Tonight for
Tonight in the Czech Republic.
It's morning, right?
it's late night here.
Yeah,
yeah, so hopefully see you in 2 weeks from now. And have a great day.
Yeah, thank you very much.
Yeah, Vivek seems to be the best weather.
Everyone.
Yeah, thanks,
Yeah, that's
everyone.
right.
Yeah. We'd love to hear about what, some speaker suggestions and so forth.
All right.